Hello viewers, we were talking earlier about the p block elements and the physical properties, how they are varying along the period and how it is varying across the group from going down the group, that was being discussed. We have also talked about the diagonal relationship between the elements, how the similar properties has been revealed in the two elements which are present in the periodic table diagonally. So, such type of discussions are now being continued today about the hydrides of the p block elements, oxides of p block elements and oxyacids of the p block elements will be discussed in detail. Some of these elements of the p block and their compounds are of vital importance in our daily life. See the nitrogen. Nitrogen is used in the manufacturing of ammonia, nitric acid and the fertilizers. Oxygen is present in air and is must for life and combustion processes. The covalent hydrides are formed when the p block non-metals reacts the hydrogen by sharing its electrons. Elements with high electronegativity value from as low as 1.5 can form covalent hydrides. Generally, their acid strength increases from left to right and from top to bottom. Group 13, the hydrides of boron, the B2S6 is an example of an electron deficient hydride. In group 14, carbon is interchangeable with silicon, germanium and tin. In this reaction, how the hydride is being formed? It is a hydride of carbon methane. It can be replaced with the silicon, germanium and tin. The hydrocarbon is a compound that consists only of the two elements, the carbon and hydrogen. It is again the hydride. The hydrocarbon can be arranged in a straight or branched chain and ring structures also. Very long chain can be formed of the hydrocarbon. There is no apparent limit to how many chains of carbon hydrogen can be formed. In the group 15, all the elements form volatile hydrides. Nitrogen can be replaced with phosphorus, arsenic and antimony, as nitrogen is forming here NH3, phosphorus will form PS3, arsenic will form ASS3 and antimony will form SbS3. Such type of hydrides can be established. Nitrogen also forms hydrazine N2H4, dinitrogen tetrahydride and hydrozoic acid N3H. Ammonia is prepared by the Haber process, is the major process for preparation of ammonia. These are the structures of the hydride. The hydrazine is prepared by the action of sodium hypochlorite on ammonia in presence of gelatin. This is sodium hypochlorite which is going to react with ammonia in presence of gelatin. Then this NH2Cl is again going to react with sodium hydroxide and form this N2H4, the dinitrogen tetrahydride. The hydrogen azide or hydrous acid of HN3 is unstable and decomposed on heating. This is the reaction for decomposition where it is being decomposed in hydrogen and nitrogen, the constituents. It is slightly more stable in aqueous solution and behaves as weak acid, forming salts known as azides, the sodium azide as NaN3. Group 16, the reaction is represented where the oxygen can be interchanged with the sulfur, selenium and tellurium. It is the hydride of oxygen. Similarly, S2 has been formed and selenium and tellurium also react similarly. All hydrides are volatile. S2O is least volatile and S2S is most volatile. Bond angle decreases down the group due to gradual decrease in the value of electronegativity, and it is the periodic property from going down in the group, the electronegativity is going to decrease. Thus, bond pair of electron moves away from the central atom and the bond pair repulsion decreases. This bond pair repulsion means it is the valence shell electron pair repulsion theory, where the maximum repulsion is being revealed between the lone pairs. The average repulsion is between the lone pair and bond pair, and very less repulsion is seen with the bond pair and the bond pair what is established here. This is the way how it is going to decrease. The bond angle is decreased from 104 degree to 90 degree on going ahead for the hydrides of oxygen, sulfur, selenium and tellurium. The group 17 is composed of the halogens and it is the formation of the hydride of the halogen. This X, the representation for the halogen can be replaced equally for the fluorine, chlorine, bromine or iodine to get prepared about the 2HF or HCl, HBr or HI. Reaction with fluorine is very fast. It is because fluorine is the most electronegative element. It is having largest electronegativity value. The reaction with chlorine is rapid in presence of light. The reaction with bromine occurs more slowly as compared to the two, the fluorine and chlorine. The hydrogen halides are covalent in the gaseous state, but in aqueous solution they get ionized and we have as a strong acid, except HF, because this HF is a weak acid having the dissociation constant value 3.2 at 25 degrees centigrade. The term hydrogen chloride fundamentally differs from hydrochloric acid, and we usually used to say that it is HCl and think about the liquid form of the hydrochloric acid, but there is slight difference. The former is a gas at room temperature and reacts with water to give the acid. However, HCl often means hydrochloric acid, not the gaseous hydrogen chloride. This is the bond distance between hydrogen and chlorine. It is 127.4 picometer, and it is the structure of this, the hydrogen and the chlorine. On a physical level, HCl gas is a yellow green gas and HCl acid is a clear solution. As fluorine is the most electronegative and hydrogen fluorine bond has maximum ionic character, hence hydrogen fluoride HF should be the strongest acid. However, the reverse is true, it is a weak acid. Why does it happen? There are many ways to understand it. Let us see one by one. Very strong hydrogen bonding exists between the hydrogen fluoride molecule and water molecule. It is the intermolecular hydrogen bond formed between the hydrogen fluoride and water molecule. So, it does not want to let go the hydrogen easily and needs large amount of energy to break the bond due to the intermolecular hydrogen bonding. It causes less dissociation and thus hydrogen fluoride is a weak acid. This effect does not occur in the other hydrogen halide. Let us see the other way to learn it. Fluorine has a small ionic size which strongly concentrates the negative charge. This negative charge is willing to hold on to the positive hydrogen, that is proton, more strongly as compared to the other halides. Because of its small size, negative charge and attraction, what will happen? Hence, it is also discussed that hydrofluoric acid is weak, not because ionization is weak, but because the ions formed bind themselves together very strongly. It is another reason. See the third reason. The entropy decreases dramatically when hydrogen fluoride reacts with water. It is particularly noticeable with hydrogen fluoride because the attraction of a small fluoride ions produced imposes significant order on the surrounding water molecules and nearly hydronium ion. The effect decreases with larger halides. This is the structure of hydrogen fluoride, and this structure is representing the intermolecular hydrogen bonding. This bond is the hydrogen bond with the dotted line, and it is the covalent bond between the fluorine and hydrogen. It is the characteristic fundamental property of the hydrogen bond that it always appears in presence of a covalent bond and is able to form large aggregation of the molecule. That is why it is having a large variation in the physical properties of the molecule. Let us discuss about the oxides of p block elements. Oxides are chemical compounds with one or more oxygen atoms combined with another element. Oxides are classified as acidic, basic, amphoteric or neutral on the basis of their acid base characteristic. An oxide that combines with water to give an acid is called acidic oxide. For example, group 14 to 17, the oxides like carbon dioxide, sulfur dioxide, sulfur trioxide, these are all acidic oxides. The oxides that give a base in water is known as basic oxide, that is like calcium oxide, magnesium oxide, sodium oxide. The amphoteric solution of a substance can chemically react as either acid or base, for example, alumina, the aluminium oxide, silica, the silicon oxide. So, these oxides of calcium, magnesium, these are all the basic oxides, and this oxide is the acidic oxide of the group 14 to 17, the carbon dioxide, sulfur dioxide and sulfur trioxide, and the third category is amphoteric of alumina and silica. However, it is also possible for an oxide to exist not as acid, base, amphoteric, but completely neutral in nature. Neutral oxides are there in the p block elements: carbon monoxide, nitrous oxide, nitric oxide. These oxides are neutral in nature. In group 13, all elements form oxide of type M2O3. Thallium also form the monoxide. On moving down the group, the basicity of the oxide increases along with the increase in metallic character of the element. Thus, B2O3 is acidic, Al2O3 and Ga2O3 are amphoteric. However, the oxide of indium and thallium are basic in nature. So, in the period, the characteristic property is being varied from acidic to amphoteric and then changed to basic. The oxide of thallium is strongly basic. It dissolves in water, forming thallium hydroxide, which possesses the similar strength to that of the potassium hydroxide. The oxide of aluminium is amphoteric oxide. When it reacts with an acid showing basic property and react with alkali showing acidic property. It has been revealed in the reaction as alumina is reacting with the sulfuric acid and it is forming aluminum sulphate, and it is the basic nature, and when it is going to react with the base sodium hydroxide, it is forming sodium aluminate, it is revealing the acidic nature. So, it is the property of the aluminum oxide to be amphoteric as basic and acidic nature has been revealed. The aluminum oxide occurs naturally as emery. Anhydrous aluminum oxide exists in two forms, alpha aluminum oxide and gamma aluminum oxide. Unlike alpha aluminum oxide, the gamma aluminum oxide is soluble in acid, absorbs water and is used in chromatography. Let us come to 14th group. The oxides of carbon involves p-pi bonding and forms colorless and odorless gases like carbon monoxide and carbon dioxide. The carbon monoxide is neutral but highly toxic. This is worth talking that it binds to the hemoglobin in preference to oxygen. Thus, oxygen carrying capacity of hemoglobin decreases and causes less availability of oxygen to the tissues. Carbon monoxide evolves a considerable amount of heat on burning and is an important fuel as in producer gas, can be used in water gas and coal gas. Carbon dioxide is greenhouse gas. It causes global warming, means it is one of the gas responsible for rise in temperature on the globe, on the planet. It can be liquefied under pressure and the solid form is called dry ice, the solidified carbon dioxide, and this dry ice is used as fire extinguisher. Silicon, germanium, tin and lead, all of them are going to form the dioxide of MO2 type, means SiO2, GeO2, SnO2 or lead oxide. This SiO2 silica is very unreactive in nature. It reacts only with hydrofluoric acid and sodium hydroxide. The dioxide of germanium, tin and lead are solid. Their basicity increases on moving down the group. Germanium oxide is acidic, stannic oxide is amphoteric, lead oxide is basic in nature. The same phenomena has been discussed in the previous group also. The lower oxide, germanium oxide, stannic oxide and lead oxide are more basic and ionic as compared to higher oxides. Lead also forms a mixed oxide, that is red lead Pb3O4. The nitrogen group, the group 15, as nitrogen can form p-pi multiple bond with itself or with the oxygen. Thus, oxides like N2O3, dinitrogen trioxide and dinitrogen pentoxide exist as monomers, while the analogues, the compound of phosphorus, arsenic and antimony exist as the dimers. Group 16, sulfur, selenium, tellurium and polonium all form di and trioxides of MO2 and MO3 type. Sulfur dioxide behaves as reducing agent and oxidizing agent depending on the other reactant present with it. It is working as a reducing agent here with the potassium dichromate in presence of sulfuric acid is working as a oxidizing reagent, and here this sulfur dioxide is going reacted which forms the chromium sulphate, potassium sulphate. The function as oxidizing agent here, SO2 plus H2S is going to form sulphuric acid. So, such type of behavior of sulfur dioxide, the oxide of sulfur has been revealed. The next oxide of sulfur is sulfur trioxide, is used to manufacture sulphuric acid. It is an acidic oxide and a powerful oxidizing agent also. This is the reaction of sulfur dioxide to form the sulfurous acid and sulfur trioxide to form the sulphuric acid. Chlorine hexoxide Cl2O6 is prepared by action of ozone on chlorine at low temperature. It is a red liquid and dissolves in alkalis producing chlorate and perchlorate. This is the reaction of chlorine hexoxide, where it is going to produce this chlorate and perchlorate in combination. The chlorine heptoxide Cl2O7 is prepared by action of phosphorus pentoxide on anhydrous perchloric acid at 263 Kelvin. It is phosphorus pentoxide, the P4O10, which is going to react to form this HPO3 perchloric acid. It is a colorless oil when explodes on heating or striking. Oxyacids or oxoacids are also known as ternary acid, contains 3 elements only: hydrogen, oxygen and a non-metal as a central atom. Till now we have discussed detail about the hydride and the oxides. It is the another characteristic, that is the formation of oxide or oxyacid or oxoacids. Hydrogen lies on the edge of molecular structure. They all have oxygen that bridges between hydrogen and the central atom in oxyacids or oxoacids. These oxyacids have at least one hydrogen atom bound to oxygen that can dissociate to produce H plus ions, the hydrogen ions. These are acid because bond between hydrogen and oxygen is weak. The hydrogen oxygen bond breaks with the formation of hydrogen ion and a polyatomic anion. Boric acid H3BO3 is also known as the hydrogen borate or boracic acid. Like silicic acid, it is also pronounced as the boracic acid. It exists as colorless crystal or white powder which is soluble in water. It is weak monobasic Lewis acid of boron. The boric acid is prepared by reacting borax with HCl. This is Na2B4O7. This is borax is reacting with the HCl forming H3BO3, the boric acid, along with sodium chloride. This boric acid is widely used as an antiseptic. It is used as insecticide. It is good flame retardant, and not only this, it is neutron absorbent and used as an eye wash. This is the structure of the boric acid. In the ball model, this is the presentation for the hydrogen. Then this hydrogen is on the periphery. It is the presentation for the oxygen, and the central atom is of the boron. It is depicted here. This is the structure of the boric acid. This is the way how the cyclic structure appears. The other oxyacids of boron are metaboric acid HbO2 and tetraboric acid H2B4O7. For a long time, it was impossible to obtain pure carbonic acid. I have switched to the next group of the carbon. At room temperature, it was very difficult. What happened in 1991, NASA scientists succeeded to make first pure carbonic acid by exposing frozen mixture of water and carbon dioxide to high energy radiation and then warming to remove excess of water. And this is the way how the pure carbonic acid was being formed. Water free pure carbonic acid is highly stable in its gaseous phase, but presence of a single molecule of water in carbonic acid decomposes it into the constituents carbon dioxide and water. So, the stability is very poor as long as the pure carbonic acid is concerned. The carbonic acid exists for only a fraction of second when carbon dioxide gas dissolves in water before changing into proton and bicarbonate ion. Despite its short life, however, the carbonic acid imparts a lasting impact on Earth's atmosphere and geology as well as on the human body. This carbonic acid is used in soft drinks, inexpensive and artificially carbonated sparkling wines and other bubbly drinks. It is the only acid excreted as a gas by the lungs of the human body. The carbon dioxide reacts with water to give carbonic acid. This is the reaction of carbon dioxide with water forming carbonic acid, and this is how it is getting dissociated. This dissociation constant for this process is 4.5 into 10 power minus 7. However, this carbonic acid is getting dissociated with this constant 4.7 into 10 power minus 11. These are the two values. The carbonic acid is weak acid with low dissociation constant, but it is stronger than acetic acid and formic acid comparatively. It is also called acid of air or aerial acid. This is the structure of the carbonic acid. It is hydrogen, and these atoms are representing oxygen, and in the center it is carbon. This is the structure bonding for this carbonic acid. The oxyacid of silicon, the next element to carbon, is called silicic acid. The compounds having silicon attached to oxide and hydroxyl group. Some simple silicic acids have been identified, but only in very dilute aqueous solution like metasilicic acid H2SiO3, orthosilicic acid H4SiO4, disilicic acid H2Si2O5 and pyrosilicic acid H6Si2O7. So, these are the acids of the silicons, the oxyacids. The silicic acid can be produced by the acidification of sodium silicate in aqueous solution. In the ocean, silicon exists primarily as orthosilicic acid H4SiO4 naturally. The silicic acid is created near the ocean surface by a non-biological process involving water as process of hydrogen naturally. It is a natural process where quartz and water is getting combined naturally to form the silicic acid, and here the silica in presence of water is getting converted as orthosilicic acid, the natural processes of formation of silicic acid. The reaction of silicic acid are difficult to control. Partial dehydration to metasilicic acid is challenging because the reaction typically progress all the way to silicon dioxide and water. This is the structure of the metasilicic acid. The structures of the silicic acid: when the silicic acid are heated, it forms an active form of silicon dioxide, also known as the silica gel, which is usually required for removal of moisture from the surrounding. The cyanic acid is colorless, poisonous, volatile liquid acid that hydrolyzes rapidly to the ammonia and carbon dioxide. It is used to prepare cyanates, that is the salt or ester of cyanic acid. The isocyanic acid is colorless and poisonous. Simplest stable compound contains carbon, hydrogen, nitrogen and oxygen. It is prepared by protonation of the cyanate anions. Usually potassium cyanate is used by either HCl gas or oxalic acid is getting reacted. This is the reaction for formation of the acid. The isocyanic acid hydrolyzes to carbon dioxide and ammonia. This is the reaction with water, and it is going to form carbon dioxide after getting hydrolyzed along with the ammonia. The cyanic and isocyanic acid are isomers of fulminic acid and an unstable compound. The fulminic acid is an organic acid and is isomer of isocyanic acid. The salt of fulminic acid, for example, mercury fulminate, is very dangerous and used as detonator for other explosive. The vapors of fulminic acid are also toxic. This is the structure of the acid, the ball model and simple bonding. It is the presence of hydrogen. In the middle there is carbon. The oxyacids of nitrogen are nitric acid HNO3, which is also called aqua fortis or spirit of the niter, and nitrous acid. These are the two acids HNO2 and HNO3. Nitric acid is colorless. It is very corrosive liquid, often take on a slightly yellow color as a small amount of NO2 is formed by photochemical or thermal decomposition, and this is the process where nitric acid is going to form the NO2 after the thermal decomposition or photochemical reaction, which is causing the yellow color in acid. The density of concentrated nitric acid is 1.42 grams per milliliter. Nitric acid is synthesized by the Ostwald's process at 700 degrees centigrade in presence of platinum rhodium catalyst. This is the reaction of ammonia in presence of oxygen, which is going to form nitric oxide. This nitric oxide reacts with oxygen form nitrogen dioxide, and this nitrogen dioxide combines with water forms nitric acid. In first step, catalytic if specific for nitric oxide formation is taken, otherwise NH3 is oxidized to nitrogen. This process may take place. So, in order to control it, the catalyst is required. It is an excellent oxidizing agent, particularly when hot and concentrated. Nonmetals usually oxidizes to their highest oxidation state and forms nitrogen dioxide for concentrated acid and nitric oxide for dilute acid. This is the reaction, and this carbon is getting reacted with nitric acid, and nitric acid is a strong acid, get completely dissociated in the dilute solution. It is the formation of hydronium ion after getting dissociated. A mixture of concentrated nitric acid and hydrochloric acid in proportion 1:3, means 1 part of concentrated nitric acid and 3 parts of HCl is constituting aqua regia, which is having the capacity to dissolve the precious metals gold and platinum. Mainly used in manufacture of ammonium nitrate for fertilizer and production of plastic, drugs and explosives. Particularly, it is used for preparation of explosive nitroglycerin, TNT, the trinitrotoluene, nitrocellulose, and it is also used as oxidizer in liquid fueled rockets. The nitrous acid is the next acid of the nitrogen. The oxyacid, it is a weak monobasic acid. This nitrous acid is very unstable and exists only in the aqueous solution. It is prepared by dissolving dinitrogen trioxide in water like this. This N2O3 dinitrogen trioxide is going to form nitrous acid. Nitrous acid readily decomposes into the constituent NO and NO2, nitric oxide and nitrogen dioxide like this. This is the decomposition reaction of nitrous acid. It is the structure of the nitric acid and the nitrous acid. It is the ball model of the nitric acid and the nitrous acid. Next in the series of the oxyacids is the phosphoric acid or orthophosphoric acid H3PO3. It is a non-toxic tribasic acid. It occurs as rhombic crystal or as a viscous liquid. Both are deliquescent. The crystals melt at 42 degrees centigrade. This phosphoric acid has a specific gravity 1.834 at 18 degrees centigrade. This phosphoric acid is soluble in alcohol and highly soluble in water. Orthophosphoric acid is prepared by dissolving phosphorus pentoxide P2O5 in water and boiling the solution. This phosphorus pentoxide, this P4O10 is going to convert into the phosphoric acid after boiling. It forms orthophosphate salts with either 1, 2 or all the 3 of the hydrogens replaced by some other positive ion. When this phosphoric acid is heated to about 225 degrees centigrade, it dehydrates to form pyrophosphoric acid H4P2O7. At still higher temperature, metaphosphoric acid HPO3 can be formed. There are 2 processes for manufacturing of the phosphoric acid. The first one is the wet process. The phosphoric acid is produced from phosphate rocks. This is the composition of the phosphate rocks used for the wet process by the addition of concentrated sulfuric acid in a series of well stirred reactor. This is the reaction of the phosphate with the sulfuric acid in the reactor. This is formation of phosphoric acid. It forms phosphoric acid and calcium sulphate. Calcium sulphate is usually known as gypsum plus other insoluble impurities. The water is added and the gypsum is removed by filtration along with other insoluble material like silica. This is the way how it is being purified. Fluoride is later removed by evaporation process. So, a pure form of phosphoric acid can be obtained. So, it was the wet process. The another process of formation of phosphoric acid is thermal process. Initially, phosphorus is sprayed into the furnace and is burnt in air at 1800 to 3000 Kelvin, that high temperature. This is the way how it is getting burnt in the furnace. This form phosphorus pentoxide. The phosphorus pentoxide is hydrated and this phosphoric acid being obtained. This phosphorus pentoxide is hydrated to phosphoric acid, somewhat similar to the previous process, but it is due to the burning of this phosphorus in the process at the temperature, high temperature, that is why it is known as the thermal process. Thermal process forms more concentrated and pure form of phosphoric acid as compared to wet process. Wet process forms less pure phosphoric acid and is used to manufacture phosphate fertilizers. The phosphoric acid is essential in the body organism as the constituent of bones and teeth, as well as in many metabolic process of carbohydrate, fat and protein. Phosphoric acid is used to acidify food and beverages, remove rust of iron, component of home cleaning product and also used in dentistry. This is the structure of the phosphoric acid, pyrophosphoric acid. The pyrophosphoric acid or diphosphoric acid is colorless, odorless, hygroscopic and is soluble in water, diethyl ether and ethyl alcohol solvents. When phosphoric acid is heated gently about 220 degrees centigrade, it loses a water molecule to form pyrophosphoric acid. This is the pyrophosphoric acid formed from the phosphoric acid. The pyrophosphoric acid or diphosphoric acid is colorless and this is gently prepared by heating at 220 degrees centigrade. It loses water molecule to form the pyrophosphoric acid. It is when heated to red hot forms metaphosphoric acid like this. The known metaphosphoric acids are characterized by cyclic molecular structure. This is the structure of the phosphoric acid in these two forms. We have discussed about the hydride, oxyacids and oxides of the p block element, which have been discussed in detail about their formation, and some of the major applications of these materials has also been discussed. And by the next episode, we shall be talking about the formation of the another oxyacid, the sulfuric acid, borazine, borazole, borazolene. Such type of materials of the p block element will be discussed in the detail. Thank you.